So let's start covering today's material. You'll notice that in your lecture notes, you have sections to read. And like I said, some of the material that I cover is going to be in those sections, and some of it will be from other sources. So don't be afraid if you don't see everything in the lecture notes. If it's not in your book, don't be afraid. I probably got it from different books. Okay? You don't have to read the notes before coming to class, because we're going to go over them. But it would help if you do, because at least you'll be a little bit prepared. I don't care if you do or you don't, but if you do want to be a little bit prepared and you want to know what we're going to talk about, then maybe you can at least give them a little bit of a look. Okay? All right. Let's talk a little bit about our sample spaces and our outcomes and all that stuff. So let's first suppose that we are measuring the resistance of a thin copper wire. This is the example I have on the notes. We're measuring resistance of a copper wire. That's it. Copper wire, you throw a current on it, and then you measure its resistance. Let's say that we can control the voltage, we can control the current, and we know the geometry of the wire. So we know the length, we know the diameter. So we can control voltage, we can control current, and then we know the length, and we know diameter. So we know geometry. But let's say that you make 5 different measurements with the same voltage, the same current, and the same geometry. But for those 5 different measurements, you get slightly different results. Like maybe at the 3rd or 4th decimal point, your results are a little bit different. Why is that? You don't have to know anything about electrical engineering, but just give me your best guess. Why is that?
Human error.
What?
Percentage of error.
And where does that error come from?
Just human error.
Okay, it could be human error. Okay, that could be one option. What else?
The conditions, like if it's humid or whatever.
Ambient conditions, humidity, right?
The reading.
Sorry, the reading, exactly. The reading of data, the instrumentation, right? I think somebody said something online.
I was going to say the inconsistency in the machinery, which is more or less the same thing.
Perfect. No, that's great. That's great. Inconsistency in the machinery. I like that word, inconsistency. Can you tell me what that means?
Well, generally we try to make things that run exactly the same way all the time, but in reality that's just not possible. We can only get things to run within like almost the same all the time. So like
why is that? You're on a roll here, so why?
That's a good question. I don't know.
It's okay. That's exactly the point of this class, right? You want to make sure that things are repeated exactly the same, but they're not, and that is why you have to take 3 credit hours of this in order to graduate somehow. Okay, so good job, Christian. You've already mentioned some variables that we didn't consider, temperature, right, or pressure or humidity, just like conditions of the environment, variations in the measuring and instrumentation, loose connections in measuring devices, that's a good one, thank you, Renee. Right, all these things are going to cause variability. Some other examples I have in my notes are impurities in the chemical composition of the wire. So as another thing, chemical composition can change as a function of ambient temperature, even as a function of time. And then current source drifts. You can tell that I copied that straight from the book because I don't know what that means. But those are all different things, right, that can cause variability in our own readings, okay? Whenever we have variables that we cannot control, such as ambient temperature, maybe we can try to control the temperature in this room, but we're not going to control it, to the dot, right? There's always going to be some sort of inconsistency. Right now, if you take some magical thermometer that measures temperatures at points in space, and you measure the temperature right here, and you measure the temperature, let's say right there, it's going to be different. Why is that? Because, well, I have my own body heat that I'm, that's influencing the environment. Even that reflection of the light has its own heat that's also influencing the temperature. There's all these things, right? So these variables that we can't control are what we're going to call noise. So let's start with a simple definition, and that is noise, N-O-I-S-E. And we say that noise represents all the variables that we cannot control. Variations in temperature, variations in pressure, variations in humidity, all those things are what we call noise. They're going to generate noise. And the purpose of a good statistical analysis is to be able to get rid of that noise. In other words, we are going to, yes, I can, except that I don't know where the microphone is. I think that's the microphone. I'm pointing to the roof. Good. Can you hear me better now? I'm yelling, so obviously. All right, I'm going to try to speak as loud as I can. Sorry, in-person students, if this feels awkward, but I want my online students to be able to hear me, okay? So, I sound fine just echoing. I actually sound echoey here. We can hear the echo. It's the classroom. I'm sorry, it is the classroom. Another reason why I prefer to teach from my house, I have my own equipment. It's a little bit clearer, you know. Anyway, the whole point of a statistical analysis is to be able to get rid of that noise. And we do it by taking different measurements. You know, we can take, let's say, different wavelength measurements. And even though we have noise giving us different values at different measurements, I don't like that autofocus. Give me a second here. There we go. Even though we have noise, we can use a little bit of statistical intuition to more or less find out what our actual value is and get rid of this noise. Obviously, this is a very simplified example where everything kind of tends towards an average value, and you can find the average value visually very well, but that is what we're going to do. Even though it's a simplified, this is what we're going to do. We're going to take different measurements. We're going to try to get rid of that noise and find the actual value that we are, that we're actually looking for. Okay? The outcome of one experiment, I already defined experiments in the last class. The outcome is essentially a function of your variables that you can control. We call that input, and the variables that we cannot control, we call those noise. So noise and input end up producing the output in an experiment. Okay? So that's kind of what a schematic of what we're going to be looking for. We have an input, which is stuff that we can control, voltage, current, geometry, and the idea, right? The idea would be to get output from that input. However, we're going to have noise that's going to affect our measurements. So our output will actually be a function of input and noise. Okay? Can anybody give me an example of any experiments you can think of, and what would constitute as input, what would constitute as noise? And I'm going to sit down. Anything. Remember, an experiment can be anything. It doesn't have to be a lab experiment. Yeah?
Crushing a concrete cylinder.
Crushing a
Measures
concrete cylinder.
Compressive strength.
That's good. That's good. What would be the input? What would be the noise?
So the input would be the pressure from the machine
Okay.
breaking down the cylinder.
That's good. Good.
And the noise would probably be anything that's contaminating the concrete, or
Good.
anything that, or the machine itself not being extremely accurate.
Good, good. So chemical composition of the concrete, which affects its resistive properties, right? At different points, concrete will have different resistance, but also inconsistency in the machinery itself. Good. What was your name again?
Michael.
Good job, Michael. Good answer. Good. So in order to more or less organize, perhaps in a visual way, maybe even in a mathematical way, in order to organize our input, our output, and our noise, we're going to define sample spaces as that space where all of our outputs are contained. And Renee has another example, which is measuring earthquakes. Noise could be anything else that causes movement, such as an airport close by. That's absolutely right, right? Noise is anything else that causes movement that we are actually not controlling and that we don't really want to take into account, but sadly we have to. Good job, Renee, as well. So I already mentioned last time that a sample space was simply, graphically speaking, a box where all the outputs are located, right? So I like to use a graphical method for my sample space, just because it's a little bit easier than math. But it can be a box, it can be a list, it can be a table, just anywhere, anything that contains all of the outputs in an experiment, all possible outputs in an experiment. Now we're going to be dealing with two types of sample spaces. We are going to deal with discrete sample spaces. And discrete sample spaces are those that are finite or countably infinite. I know that doesn't mean much to you when I say it like that, so let me just give you an example. If you can count the number of outputs, even if it's an infinite number, if you can count them, this is my first output, this is number 2, number 3, number 4, it's discrete. Why? Because if you can count it, then that means that there are clear gaps in between each output. For example, this sample space can contain 1, 2, 3, 4, 5, 6, 7, 8 outputs. And anything in between those 8 outputs isn't really an output, it's a gap. Our outputs can be numbers, they can be colors, they can be anything you want. Let's call them numbers. 1, 2, 3, 4, 5, 6, 7, 8. One example of a discrete sample space, let's say number of students in a classroom at a time. Well, right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 students in this classroom. Maybe next time I'll have 8 students. Maybe next time I'll have 20. There will always be a clear gap between 1 student, 2 students, 3 students, because I can't have 1.5 students in a classroom at a time. I mean, I can, but it's not going to look nice, right? So whenever you have clear gaps in between your number of outputs, we say that the sample space is discrete. Of course, this is different from a continuous sample space. A continuous sample space is something that you cannot count. In other words, instead of a number of possible outcomes, you have a region, an area of possible outcomes. A continuous space, instead of little boxes inside my big box, I would have big areas inside my big box. And anything inside those areas would represent a sample space. One example of a continuous sample space would be something like measuring current or measuring voltage. Your voltage can be 1, 2, maybe 1.5, 1.496. It really depends on the instrument itself. But physically, it could be basically any real number, any number on the real number line. So because of that, there's no clear gap in between your different outcomes. Whenever we talk about continuous sample spaces, I do want to keep in mind that obviously the precision of your measurement is going to depend on your instrument. So for example, if I'm measuring my own weight, my scale will determine the precision, right? I can have maybe 1 decimal point of precision, maybe 2 decimal points, that's too much, maybe 1 decimal point. However, physically speaking, my weight can be any real number within the appropriate, within the adequate range for males my size and height, whatever. Right, so continuous sample spaces have essentially infinite number of possibilities that cannot be counted. Discrete sample spaces have a finite or infinite number of possibilities that can be counted. Again, discrete, you can count. 1, 2, 3, 4, 5. Red, blue, yellow, orange. Continuous, it's a real number. 1.486, 2.597. Yeah?
This is like an example question with an example. You remember a couple of weeks ago there was a Chinese rocket that hit the Earth. They couldn't calculate where exactly it would hit the Earth.
Yeah.
So that would be continuous because they couldn't calculate it, or that would be the discrete because at the end they figured out where exactly it's going.
It will be continuous because the location at which the rocket would hit, remember, it's an area, right? It's like within this area, at any point, that's where the rocket would hit. Obviously, that area would get smaller and smaller as the rocket would get closer and closer. As it's actually a piece of a rocket, right?
Yeah.
So it would get closer and closer, but it's still continuous, right? Because it's still a continuous area. There's no gaps in between, right? So it is an example of a continuous sample space, and that's actually a really good example because that is statistics right there, right? It's like if it was just a matter of physics, that okay, we got our classical mechanics equations, we plug them in, we would know exactly where that piece of rocket was going to hit. But of course, there's so many variables that we cannot consider, such as, temperatures, pressures, currents in the atmosphere, currents in the whatever is below the atmosphere, all those things, right? So we had to use statistical methods. Obviously, when I say we, I mean the collective we as in humanity, not me. I wasn't a part of that. So yeah, that's a really good example. Another example of something that could be discrete could be I was talking about weights earlier, and like I said, if you're limited by your scale, then your weight could be discrete because I can say my weight can be 190.1, 190.2, 0.3 because my scale does not measure anything in between. But we know that physically, it can be actually any number between 190.9 and 190.8 or something, right? So we're going to get some examples of this. In this class, we are going to deal with both discrete and continuous sample spaces, but you'll notice that as the class progresses, I'm going to focus on discrete because anything that we learn for discrete sample spaces, we can expand into a continuous sample space. The theory is actually the same, except that one of them, it's counting, so you just add up, The other one is an infinite area range, so you integrate. And we'll learn about that later, but you'll notice that even though we're going to deal with both, as the class progresses, we'll focus more on the former and less on the latter, just so that we can focus on new material and not have to apply it to everything. I have some examples in my notes of what would constitute a discrete sample space, and the two examples that I use in the notes are actually the two classical examples, which are flipping a coin and rolling a die. In fact, these are two classical examples because those are the examples that are most commonly used in statistics classes. They're easy. We're all familiarized with them. We all know what the outcomes could be. And because of that, things are relatively easy to use. I'm going to do some examples today, and you'll be like, okay, yeah, that's interesting. I'm going to do more examples on Wednesday, and you'll be like, okay, yeah, we get it. I'm going to come up with more flipping coin examples on Monday, and you'll be like, can we do something else? You'll notice that by the end of next week, you'll be tired of flipping a coin, but that will be that is my go-to example for this class, because everything we cover in this class can be explained somewhat easily with a coin flip example. So I apologize in advance, but I will be using that example a lot. Yeah?
So what are the spaces in between for flipping a coin?
In a discrete sample space, there's nothing in between. So that's why I kind of just use black here, so nothing.
Okay.
Yeah. But in a continuous, there's always an outcome in between. So you flip a coin, what are your outcomes? Okay, so let's say that your sample space consists of two outcomes, heads and tails. You roll a die, just one die. What are your outcomes? Let's say it's just a standard die, standard 6-headed die. 1 through 6. Okay, so 1, 2, 3, 4, 5, 6. If you roll a single die, there is no 2.5, right? It's just 1, 2, 3, 4, 5, 6. Good. In terms of continuous, typically physical properties are continuous, so things such as mass, velocity, and any other physical properties that you can think of are typically continuous, I guess, would constitute a continuous sample space. I'm trying not to use words that I haven't defined yet, so I got to make sure I use words that I've already defined, so sample space, okay? Let's do a quick example. And surprise, surprise, let's say that we're flipping a coin, but at this time, let's say that we flip a coin twice, okay? So for now, we're going to flip a coin twice. Twice means 2 times. I don't even know that. What does your sample space look like? What are the possible outcomes if you flip the coin twice?
There should be 4 possible.
You can get heads twice, tails twice.
There we go. So you can get heads twice. Okay. You can get tails twice. Is that it?
Heads and tails.
Heads and tails. You can get heads first and then tails. Good.
Tails and tails.
Tails and heads. So how many outcomes in this sample space?
4.
Okay. So we flip the coin. We have 2 outcomes. We flip it again. Now we have not 2 but 4 outcomes. Good. Hopefully you'll realize that there's a relationship there somewhere, but we're going to talk about that later. That is essentially what a sample space is, right? Different outcomes, even though each outcome constitutes of similar variables, right? We have 2 variables, heads and tails, but the different outcomes are combinations of those 2 variables. You can see we have heads, heads, tails, tails, heads, tails, tails, heads. I want to make sure this is clear because sometimes a lot of statistics books, especially your textbook, books don't really make a distinction between variables and outcomes. They kind of treat them as if they were one and the same, but they're not. Right? You can clearly see that you have multiple variables, but then outcomes, in this case, the outcome is a combination of those variables. Does that make sense? Okay, let's keep that in mind for the future. All right, I mentioned last time that we're going to deal with this mathematically by using sets, set operations, unions, intersections. I know you've learned all that in your school, high school or whatever, or middle school, I don't remember, but if you forgot about it, or if you were in high school many, many years ago so you don't remember, or if you didn't pay attention, that's what I'm here for, that's what today is for. We're going to review all these set operations. It is important that you understand what these operations are and how to do them before we move on to the next topic. So even if we have to spend more time on this topic, I need to make sure that all of you understand set operations. Okay? So let's first define events. We already said that an event was a subset of the sample space. This was in the last class. A subset of the sample space. And you may I'm using S for the sample space. And I want to keep that, that nomenclature for the rest of the semester. S for the sample space. So S is everything, all the outcomes. I can give you an example. Let's say that within a sample space, you can select different groups of your outcomes and lump them together into an event. Let's say that this is my sample space, this box is my sample space S, and I can take an event of that sample space here. In other words, all the outcomes inside this blue circle are going to be part of my event that I'm going to call A. I can create another event with other outcomes. Let's say that all the outcomes maybe inside this red circle are part of my event B. I made sure that those circles intersected on purpose, obviously, because now we're going to learn a little bit about the unions, okay, intersections and complements of these events. So the first set operator we're going to talk about today is the union. The union is represented with this big U sign. And essentially, it consists of all the outcomes that are included in both, in either, in this case, A or B. So union is all the outcomes that are in A or B. If you look at this sample space that I do, let me see if I have a pencil here. I do not. Does anybody have a pencil that I could borrow?
It doesn't have an eraser though.
Doesn't matter. I don't make mistakes. I'm kidding.
Anyway.
Anyway. Are you saying that I'm going to make a mistake?
Of course not, of course not,
Okay.
sorry.
So if we're looking at all of the outcomes, right, in A or B, it's going to be anything that is in A plus anything that is in B. Okay, so A or B just means anything in both, okay? So here, this, for example, is in A, this is in A, and this is in B, and this is in B, but we already selected it. So when I say the union of A and B, so this AUB, this is called a cup. So A cup B, it represents everything that's inside A and everything that's inside B. Even the things that intersect, they also are included. So in this case, right, my union of A and B is going to constitute of everything inside these two circles. If we can give them names, let's call this region 1, region 2, region 3, and let's say that everything else is region 4, then A cup B is regions 1, 2, and 3 in this case, just for this example. Does that make sense so far? Union, everything in either one. Or if it's in A, it's part of the union. If it's in B, it's part of the union. If it's in both, it's also part of the union. Does that make sense? Good. Our next operator, and I guess I'm going to have to draw this again. I should have just taken that eraser. But I'm too proud to admit I was wrong, so I will draw it again. And let's keep calling A the blue one, B the red one, and everything else is the sample space. We're going to talk about intersections. The intersection is typically written with a cap. And we just say A cap B. Now the intersection is anything that's in both A and B. Not A or B, but A and B. So in order for something to be part of your intersection, it needs to be in both of these events. If you look at here, once again, let's call these regions 1, 2, 3, and 4. What region is in both A and B? 2. Good. So the intersection of A and B would be only this region, which for this example would be region 2. Good. Don't memorize 1, 2, 3, 4 or anything, because the event can be anything that I want it to be, right? It doesn't have to be circles, it can be something else. As soon as I memorize that, 1, 2, 3, and then just write it down on the test. So, wait, what's 1, 2, 3 here, right? If there's no regions defined, okay? And finally, we are going to talk about a complement. Now the complement is a little bit easier. we typically, we find the complement not for two, but for one event, right? So we can say A, and the complement of A will be written as A prime. Now the complement is anything that is not in the event that you are studying. So if this is A prime, the complement of A is anything that is not in A. So while I'm drawing my sample space, what regions do you think would be included in the complement of A?
4, 3,
Can I say that again?
3, 4.
3 and 4. Good, that's absolutely right, because 1 and 2 are both regions that are in A. So in this case, my complement will be everything that's outside of that blue circle, everything that's outside of regions 1 and 2. Now somebody said region 4. Now I think we understand why it's actually 3 and 4, not just 4. But now that we're talking about region 4, do you think you can come up with some expression using the things you've learned, or one or more of the 3 things? Can we come up with one expression that gives me only region 4 and nothing else?
Complement of A and B.
Exactly, complement of the union of A and B, right? Because if we want 4, 4 is everything that's not in 1, 2, 3. And this is 1, 2, 3. Therefore, 4 would be just the complement of the union of A and B, yes?
So to write that, would the prime go over A and B, or just the whole thing?
That's a really good question. In this case, you can just use parentheses. So you have the union of A and B first, and then the complement of that. However, we are going to learn that there's actually several different rules that we can use that help us kind of like express this in terms of A and B individually. Yes?
So why is, when you're doing a complement, why is 3, like the complement of A, why is 3 if they overlap? Is that,
Well, remember, 3 is only this part, this little crescent. And that little crescent is not part of A, right? It's
Oh, right,
outside
right,
of A. Yeah. Oh, I wasn't showing. 3 is this crescent.
okay.
Yep. So far, so good? What's your name?
Samuel?
Samuel?
Yep.
What about you?
Quinn.
Oh, you were in my fluids class.
I was
Nice, nice. I have a lot of fluid students here, that's good. You will tell that this class is not nearly as exciting or interesting as fluids, but, you know, we deal with what we have. Good, good. Can I move on? Does anybody have any questions so far? I know it seems kind of easy, but let's make sure we understand it, okay? I know that you all understand everything, and because of that, I'm going to try to test you a little bit. Let's see, I'm going to draw my sample space. And I'm going to draw 3 events. Let's see, I'm going to call this my A. I'm going to call this one my B. See a green marker here, I'll take advantage of that. I'm going to call this one my event C. So I got A, B, C. This is the sample space. I need to define my regions just so that I don't have to force you to come here and write anything on the paper. So I'll call this 1, 2, oh, this is going to be hard. 3, 4, 5, 6, 7, 8. Okay. Now I would like for you to find the intersection of the union of A and B with C. Let me write that again, but in written form. The intersection of the union of A and B with C. What regions would be included in the intersection of the union of A and B with C? Step by step, right? Let's start first with the union of A and B, right? So what's the union of A and B here? What regions are included there?
2 and 4.
The union of A and B, is that just 2 and 4?
B 1,
1,
2,
2,
3.
3.
Oh, yeah.
Okay, good. It is hard to see. I apologize for that. Let me see if I can make this a little bit bigger.
That would be 1 through 6, right?
1, 2, 3, 4, 5, 6. Good. That's the union of A and B. So I'm going to write that down. A union B is 1, 2, 3, 4, 5, 6. Good. Now we want the intersection of all these with C. So what is C right now? What regions constitute C? 4, 5, 6. I guess that's the final answer. Good. But what regions constitute 6?
5, 6, and 7.
Yeah, that's correct. 4, 5, 6, and 7. And because we want the intersection of these two is anything that's included in both of those. So what's included in both of those? Christian and Oleg already said so, 4, 5, and 6, right? You see that 4 is here in the union of A and B, but it's also in C. 5 is in the union of A and B, but also in C. And 6 is in the union of A and B, but also in C. So the intersection of the union of A and B with C is going to be regions 4, 5, and 6. Does that make sense? The parentheses work just like in arithmetic. Right? You look at the parentheses first, then you look at everything else. And that kind of applies here, okay? Does that make sense? Good, good. Online students, my in-person students are nodding. So that means that it makes sense to them. And I would like to now figure out what is the complement of the intersection of A and C. The complement of the intersection of A and C. First of all, what is the intersection of A and C? Let's just look at this part. What's the intersection of A and C?
4 and 6.
4 and 5, right? There we go.
Of A.
Remember A, C, so 4 and 5. I know it's not very clear. My handwriting is not the best, and yet I insist on handwriting for my lectures. You can tell that I'm a very stubborn person, okay? So the complement is anything that's not that, right? So what would the complement be?
1, 2, 3, 6, 7.
Correct. 1, 2, 3, 6, 7, 8. Good. Good. Does that make sense? You find what's in the parentheses first, then you work on everything else. Good, good, good. Let's make it a little bit more complicated. Let me pick one that wasn't in the notes so that even the most prepared students have to put in some work here. By the way, do you know what type of diagram this is where I have all these circles and they overlap to show where there's intersections?
Is V or V?
Venn diagram, that's correct. Very, very useful. Venn diagrams are really useful. We are going to use them a lot in class. I don't have to define them or introduce them, but just so you know. All right, we'll call this circle A. We'll call this one B. This is the sample space. I'll call this my region 1, region 2. Everything else is region 3. I would like to know what is the union of A and B, and what is the intersection of A and B. Let's start with the union. What regions are in the union of A and B?
1 and 2.
1 and 2, okay. What regions are in the intersection of A and B? There is no intersection. So if there is no intersection, we call this an empty set. 0 with a diagonal line over it. It's not really 0, the number. It's actually it just means nothing. Empty set. Okay. If you're writing it on LaTeX or Word, then just use / empty set, and it'll give you that thing. Good. Good. So you can see that there doesn't have to be an intersection always. Sometimes your events are not going to overlap. Obviously, we're using little colors and circles and stuff like that, but the idea is that you take this and then you apply it to whatever is you're studying statistically. For example, I can say something like, okay, how many students are in the civil engineering program here? Not environmental, civil. Okay. Okay, never mind, everyone. So, how many students are in the environmental engineering program? Oh, there we go. Good, good, good. But then how many students are KSU students? Everyone, right? So if I find students that are in civil, students that are in environmental, maybe we won't have an intersection, but if I'm looking at schools, for example, then there is an intersection because you're all in KSU. So you are going to take all this, you are going to apply it to whatever it is you're studying statistically. Okay? So, that being said, let's give a little bit of rules. You know, whenever you have all these math thingies, there's always some theorems, some rules, some axioms that you want to follow. Now, I'm not going to go through a derivation of all of these, but some of these are actually relatively easy that we can see them, even just visualizing them, we can see them. The first law, we're going to call these laws. The first set law, and you don't have to memorize them, that's why all the tests and stuff are open book, open notes, but always understand them, is that the complement of a complement, so the complement of A is just A. Does that make sense? Let's think of it this way. Let's look at what's inside the parentheses. First, you look at that diagram that's on the board. What is the complement of A? What regions are the complement of A? 2 and 3. Good. And if we take the complement, that is what's not 2 and 3. So what is not 2 and 3? 1. And what is 1? A. So the complement of a complement is just whatever event you were studying. So the complement of A is A. Some students like to say that these two cancel each other out. I don't like to use that terminology because it's not really what's happening, but if that makes it easier for you to remember, then maybe you can use it. You can say that complement cancels out complement, okay? First law, I think we don't have to derive anything. I think it's clear to just see it, okay? Second law will be the distributive law. Maybe not as clear, but if you try some examples, you'll see that it works. And that is that the intersection of the union of A and B with C is equal to distributing what's inside the parentheses over the rest of the functions. In this case, it would be equal to A cap C union B cap C. So it's very similar to the distributive law for algebra, right? Where if you're doing some operation and you have something in a parentheses, you can actually, distribute it. It's the same thing, right? You're just distributing your C throughout your A and your B. So it's like you take all this and you plug it in here and also in here. Not something we want to derive here, but hopefully you've already done something like that in algebra, right? If you have like A plus B in parentheses, right? A plus B is multiplied by C, you know that that will be equal to A times C plus B times C, right? It's exactly the same thing, but for sets instead of arithmetic or algebra or whatever. Let me make sure I cross this out because this is not part of the lesson. This is just an example. But that is the distributive law, and that applies to all of our sets. Another form of the distributive law is that it doesn't really matter what is where here. So for example, you can have the opposite. You can have the intersection. So let's call it A cap B, and then union with C. And that will be equal to A union C cap B cup C. I'm using union, intersection, cap, and cup interchangeably because I want you to get used to both. But remember, cup is a union, cap is an intersection. Okay, so the distributive law pretty much applies to both. The reason I want you to know these is because sometimes you're going to be dealing with events, and sometimes it will be easier to calculate them in one way. Sometimes it will be easier to calculate them in another way. Right now, everything seems fine because we're dealing with 3, 4, maybe 8 regions. But when you're dealing with thousands and thousands and thousands of data points, you want to find the easiest way, right? And that's why I think you should memorize these different laws. After this, we have the Morgan's law. The Morgan's law talks about complements when you have unions or intersections in them. So let me just write down the Morgan's law. And what that states is that the complement of the union of A and B is going to be equal to the intersection of the complement of A with the complement of B. Oh. God, I need to find a better way to arrange my paper here. Similarly, the complement of the intersection of B is equal to the union of the complement of A with the complement of B. So the Morgan's law. So notice that it's not as simple as saying, well, this is just A prime, U, B prime, because the sign changes. It's no longer a union, it's an intersection, and vice versa. And finally, just a final law that's also very important is that the union of A and B is going to be equal to the union of B and A, and the intersection of A and B is going to be equal to the intersection of B and A. Now this one, as simple as it looks like, it's actually going to be the most powerful of the laws we're going to use, because this is going to help us come up with a lot of different statistical equations. And you need to understand that, right? Because sometimes you'll be like, wait a minute, where did that equation come from? I say, well, it comes from the fact that A union B equals B union A, and A intersection B equals B intersection B. So order doesn't matter. Does that make sense? Order doesn't matter? Good. I know it's a math review. You may be thinking, when are we going to go back to statistics? So let's give an example. Guess what we're going to do? Flip a coin, yeah. All right. Let's talk a little bit about counting and okay. Let's talk a little bit about counting, and for that, let's flip a coin. Okay. We already said that if you flip a coin, you have two outcomes. If you flip it again, how many outcomes?
4.
If you flip it a third time, how many outcomes? 8. If you flip it again, how many outcomes? 16. Again?
32,
32. Good. 64. Yeah.
etc.
120. Yeah.
256.
256. Yeah. 512. Yeah.
24.
Okay, good. If you know anything about video games and resolution, especially if you were like me, where you went to the 124 bits, you're like, wow, and then you know, then you get excited here. But do you see the pattern here? What's the pattern? If you flip a coin n times, how many outcomes?
2 times 2.
2 to the 10th.
2 to the n, right? Right, because it's 2, then 4, that's 2 to the power 2, then 8, that's 2 to the power 3, then 16, 2 to the power 4, 2 to the power 5, 6, 7, 8. Okay? So this is actually not something that is very strange. In fact, whenever you have the same outcome and then you just repeat the experiment, that's essentially how it increases, right? The number of outcomes to the power of the number of times you repeated the experiment. There's a rule for that. It's called multiplication rule. But for now, let's just try to generalize it just a little bit. So we're going to learn how to count. I know that you know how to count, so we're going to learn how to count statistically, and the easiest way to count statistically is through multiplication. Now, your book calls this the multiplication rule. I don't like to call it that because there is a statistical rule called multiplication rule, which is something else. So I'm just going to say multiplication. Okay? Now, we already know that the number of outcomes is going to be, well, you have your number of outcomes in the first experiment. And you elevate that to the power of the number of times you repeated the experiment. In the case of flipping a coin, you had 2 outcomes every time you do the experiment, and then you repeat the experiment n times, you'll have 2 to the power of n outcomes. Now that's okay if every experiment has the same number of outcomes. But what if it doesn't? Well, if it doesn't, you can still generalize this, except that instead of elevating to an exponent, you're just multiplying. Because if you look at it here, all you're doing here is you're just multiplying 2 times 2 times 2 all the way to n times, right? So 2 times 2 times 2 times 2 times 2, all the way to your letter n. But if different runs of the experiment have different outcomes, then all you have to do is write those different outcomes here. So let me give you an example. Let's say you are designing a website, and you can choose between 4 different colors, one of those 4, okay? You can choose between 3 different fonts, and you can choose between 3 different image sizes. So how many possible combinations of your website are there? You can choose 4 different colors, right? So you have 4 outcomes, but you can choose 3, you can choose 3 different font sizes. So how many, between just those 2, how many outcomes? 12, 4 times. But then 3 different image sizes. So 36, good. So the multiplication rule is, all it tells us is that in order to get the total number of outcomes, all you have to do is multiply the number of outcomes in each step of the experiment. If the steps are all the same, like flipping a coin, then it's just, your outcomes to the power of the number of times. But if not, all you have to do is multiply. So the multiplication rule tells me to multiply the number of outcomes in each step. I didn't want to do the website example because It was a little bit too simplistic. I thought of a better one. So I went with my wife to eat Mexican food, and it wasn't very good. It's actually a little bit salty. So we were both like, oh, it's too salty. And we're actually right next to Cold Stone. So my wife's like, oh, let's get Cold Stone. She doesn't talk like that, but she said, let's get Cold Stone. So we went to Cold Stone, and we wanted to build your own. And me, thinking of my students and how I can apply my life to them, I was thinking, how many possible combinations of a Cold Stone ice cream can you have? And do you know? Do you have any ideas? No? I mean, I didn't do it right there. I have a life. I wasn't like doing statistics there, but I went to the website before coming here, and there's actually a lot of different options. So you have your option of your base ice cream flavor, right? And let's just make it simple. Let's say you have only one scoop. You have your option of your base ice cream flavor, and then you have your toppings, and then you have the size, like small, medium, large, and then you have whether you're going to use cone or the like waffle cone, waffle bowl, or just the typical cup. You multiply those together, you're actually gonna get a lot, like hundreds or thousands of different options. But here's where things get a little bit more complicated. In Cold Stone, you don't just choose one topping. You can choose 1, 2, 3, as many toppings as you can. So how do we do that then? How do we find the number of possible ice cream combinations? Because now you have 15 different toppings to choose from, but that doesn't mean you have 15 outcomes, because you can choose all of them or none of them or some of them in any different order. And each one of those counts as an outcome. So how many outcomes do you have? Like, how can we find that? Factorial of toppings. I like that, and that is the answer, yes. God, why do students have to read the notes and be prepared? No, it's okay, it's true. So when you can only choose one of your number of outcomes, you just multiply. But when you have multiple outcomes and you can choose one or more than one and they can all come in different orders, you have to take the factorial. Does anybody know what a factorial is?
15 times 14 times 13.
Exactly. It's the number times the integer before it, times the integer before that, times the integer before that, until you get down to back to 1 and 0, and then the factorial of 0 is just 1. And the only reason the factorial of 0 is 1 is so that it doesn't mess up your whole equation. Because you're adding everything. I mean, you're multiplying everything. Okay, okay. Good. So when we talk about that, that style, you're not really multiplying, you're actually finding a permutation. In other words, in the case of a permutation is when you have 3 outcomes, but you don't want to just choose 3, you can mix and match them in any order. And obviously, it doesn't have to be 3, it can be any number. So consider, let's say the topping choices are A, B, and C, but you can choose as many or as few as you want in any order. What are your outcomes?
A, B, C.
A, B, C, okay.
And A, B.
Let's say you want to choose all 3 of them, just to make it simple. Let's split this up into different. Let's say you want to choose all 3 of them, just to make it simple. And you can choose them in any order you want.
CBA.
CBA?
BCAC.
BCA? What?
BAC.
BAC?
We can repeat them, right?
CAB.
CAB, we cannot repeat them. If we could, then that would be a whole different thing.
So it's gonna be 6.
It should be 6.
ACB.
ACB. How do we know it should be 6?
3 times 2 times 1 because we can't split.
Exactly. So the number of outcomes is going to be n factorial. In this case, it's 3, so 3 factorial is 6. So, good. Now that's a permutation. Now, of course, I'm making things a little bit simpler here, because here I'm saying I still want you to choose all 3 of these topics. It's just that you can choose them in whatever order. So obviously, there are other ways, and let's keep making it complicated. But just so you have it in mind, you keep in mind, you multiply when you can only choose one of your number of outcomes. You permutate, I'm not sure if that's a verb, but you permutate when you can choose all of your outcomes, but in different orders. And now, let's look at a more complicated type of counting, if that is permutations of subsets. I would like to incorporate the Cold Stone thing into the project, so you may see that. I'm not going to make you go to Cold Stone, but I may make you go to the website and figure out what options they have, and tell me how many possible ice cream choices they have. But it'll be all be in the homework when it's time. I can guarantee you that everyone's gonna have a different answer for the Coldstone thing. Like, there's gonna be many different answers, okay? I mean, I wouldn't mind getting ice cream for class. When you say for class, do you mean for all of us? Or for class as in your experience in the class, Christian? I need you to clarify that. Christian, please answer this question, otherwise I cannot continue. I need to know that when you say ice cream for class.
I'm my own
for
ice
all
cream.
of
You
us or
guys
class?
have fun.
What? Say it again?
I'm getting my own ice cream. You guys defend for yourself.
Minus 1 point.
Can you give him a 0 right now?
0? Come on. I cannot be that biased, come on. I would never do that.
Painful. But I'll have ice cream.
I got a 90, why did I get a B? I don't know.
Sorry.
You should have been less selfish. Anyway, let's say now, okay, that we have our 3 elements. So let's say 3 toppings, A, B, and C. But let's say that this time, instead of choosing between all of them, which would give you a total number of outcomes of n factorial, let's say you want to choose all the different possible combinations of only 2. So choose 2. And you want to put them in any order. So how many outcomes would you have? Or what outcomes do you have? Give me the number. What would be your outcome? You choose 2, and order matters.
AB,
AB, okay.
BA,
BA,
AC,
mm-hmm,
CA,
mm-hmm,
BC,
mm-hmm.
and CB.
How many is that?
6.
Good. Is the answer n factorial? It's actually not. The way we generalize this is by saying the permutation of 3, choose 2, is going to be equal, in this case, to 3 factorial divided by 3 minus 2 factorial. Or if we want to make it a little bit more general, if you have n outcomes and you want to choose r of those outcomes, then you will have n factorial over n minus r factorial. This is what's called a permutation of a subset. So we have multiplication. You multiply everything. If you want to choose all of your outcomes in any order, you take the factorial. If you only want to choose between a small number, a subset of those outcomes in any order, you take a permutation. Okay? If I talk too much about ice cream, I know that some of you will complain and be like, hey, we're not learning anything in engineering, all we do is talk about ice cream. So let me give you a little bit of an engineering example. And this one's actually from the textbook, so you have it on your textbook if you want. Let's say you have a printed circuit board. So I'm going to draw my circuit board here. You've all messed with Arduinos before, right? And stuff like that. So you know a little bit, no? Okay. So it's just a circuit board, right? You connect up to it, okay? And let's say you have 8 slots. 1, 2, 3, 4, 5, 6, 7, 8. And you have 4 components that you want to connect on this circuit board. So you have 4 components. 1, 2, 3, 4, and they're different components, so let me just call them 1, 2, 3, 4. I can connect any of these in any slot, but the 4 have to be connected. Now the question is, how many possible combinations, like how many permutations of this circuit board are there? Well, you have 8 total slots. You have 4 components. In this case, what would n be and what would r be? But what would n be? Just n. 8, right? Because you have 8 possible outcomes, or 8 possible toppings, okay? And R4 because you can explore those toppings, okay? So always try to bring it back to ice cream, right? In this case, your circuit board is your number of toppings, okay? And then the components that you connect to it are the toppings that you're choosing from, okay? Or that you're choosing. So in this case, you would have a permutation of 8 outcomes where you choose only 4 of those. And that would be 8 factorial over 8 minus 4 factorial. How many possible combinations? Somebody said 32. I doubt it's going to be 32. Because remember that the 4 are different. The 4 components are different.
1,600.
Yep, 1,680. Let's say you're doing the exam, and oh my God, you forgot your calculator. That doesn't make sense because the exam you'll do them from your house. But let's say that you're doing the exam, you happen to be visiting your relatives, you forgot your calculator. Your relatives are Amish, so they don't have calculators. And you don't have a car to drive to the nearest calculator store to buy a calculator. How would you solve this?
Ask
I-
Amish.
Would you multiply 8 times 7 times 6 times 5 times 4 times 6 times 2 times 1 and divide that by whatever you get from 4? No, what would you do?
I would write it out.
Okay, you write it
And then
out.
you simplify it. So
Okay,
you
write it
make-
out and simplify. Good, I like that. So I can write, for example, 8 times 7 times 6 times 5 times, and you know what? 4 times 3 times 2 times 1, that's 4 factorial, right? Okay, so let's write times 4 factorial. And this is divided by 4 factorial. And you just cancel out your 4 factorials. And you have a simpler thing to do here. 8 times 7 times 6 times 5. Okay? You do that, you get 1680. And at this point, the multiplication is a little bit easier now, right? Because now you don't have to multiply everything. You just find ways to simplify it a little bit, okay? This is going to be crucial because sometimes your calculations will be simple enough that you can actually just do them by hand. But you don't want to do the whole thing by hand. You want to make sure you make life a little bit easier for yourself. It's almost 3:15. Let's take a 15-minute break because it's a 3-hour class and I need to take a break. And we'll start again at 3:30.
Professor, can I ask you a question?